Hello, this is part 2 of getting started with ka9q radio. In this particular episode, we'll look at some selected HF or high frequency applications centered mostly upon WWV and CHU. In the first demonstration, we'll use AM demodulators in the ka9q package, and we'll stream multiple WWV and CHU channels over the local area network where we can receive them and listen to them. In the second demonstration, we'll send multiple WWV and CHU channels using IQ format, and there we'll be able to receive them in gnuradio and look at each station in a little bit more detail, where we can examine the spectrum, the time domain signal, the carrier frequency, and the carrier magnitude. And finally, we'll look at recording one of the channels using the DigitalRF package, which is an HDF5 type hierarchical data format used for storage and archive, including metadata of various signals. For details of the configuration and system setup, I'd refer you to part 1 of getting started with ka9q radio. Just as a summary, the server is a Raspberry Pi or other Linux computer that has an HF or high frequency software-defined radio plugged into it, and it sources multicast packets onto the local area Ethernet network. In this demonstration, we'll be accessing that server using SSH from the client over the Ethernet network. The client computer is running Linux and gnuradio and some out-of-tree modules depending on the particular demonstration. We'll access this using a terminal window on the client itself. And then, of course, we have an Ethernet switch so that the client and the server can talk to each other. And we'll demonstrate 3 basic applications. One using AM demodulator, encoding the audio using an Opus audio coder to send audio frames over the Ethernet local area network. Another application to send IQ samples in real time over the multicast network, where we can visualize them with gnuradio. And then a third demo where we'll send IQ samples and record them in DigitalRF format, which is a standardized format that includes metadata that's usable for these type of applications. This is a block diagram of the setup, and you can see on the right we have a Linux PC referred to as the client, and it has a mouse and a keyboard, a computer display. It's connected via Ethernet to the server, and the server can be a Raspberry Pi or it can be a Linux PC. It's running the ka9q radio software. Plugged into that Linux PC or Raspberry Pi PC is the RX888 HF or high frequency SDR receiver. In this particular application, it's connected to a 1 meter diameter active loop, and there's a 12-volt bias T that provides power to that active loop. Again, there are recommendations on how to set up the addressing, and I'd refer back to part 1 where that's discussed in more detail. Software sources ka9q radio is available from Phil Karn's GitHub. The GRRTP out-of-tree module for gnuradio is from Franco Venturi's GitHub, and the DigitalRF module is from the MIT Haystack GitHub. Support files for this tutorial that are the configuration files, some of the gnuradio application files are available on my GitHub in the Miscellaneous section. So again, refer to part 1 for initial steps on how to install ka9q software in gnuradio. For the purpose of this part 2 video, the versions being used are ka9q radio from November 13th, GRRTP from November 18th, and DigitalRF from September 27th. It's best to start the program using the command line rather than automatically using System D at startup, because running it from the command line provides feedback on how things are working and if it was successful, how many demodulators were brought up. It also provides the IP addresses of the multicast streams. To start up the HF application, we'll connect the RX888 to a free USB port on the server, and we'll run the server by changing into the ka9q radio directory. We'll then execute the radio D program with the name of the configuration file, radio D at rx888-n5eg-hf.conf, and we'll examine the output of that command to verify that it's launched correctly. In demo 1, we'll open up just a terminal on the client and we'll execute the monitor program, which will allow us to listen to the WWV audio. Demos 2 and 3 will also start gnuradio companion on the client so we can visualize and do some other functions. The HF tutorial configuration is derived from the ka9q distributed RX888 HF application, and that application can change occasionally as the ka9q software is updated. This tutorial file, the N5EG configuration version, disables most of the services that Phil put into his default application, and the N5EG version is put into the home/ka9q radio directory, where it won't get overwritten by updates that Phil may make to his software in the future. A good tip is to always save a copy of your unique configuration files in a separate directory to prevent them from being accidentally overwritten on an update. This is a snippet of the code for this demonstration within the RX888-N5EG file. The first section is labeled bracket WWV bracket. Disabled no means that it's active. The data multicast stream name is wwv-pcm.local. The mode is AM, and there are a few channels identified: 2500 kilohertz or 2.5 megahertz, 5000 kilohertz or 5 megahertz, 10 megahertz, 15, 20, and 25, which are the WWV HF frequencies, as well as 3.3, 7850, and 14670, which are the CHU frequencies. A separate section is the WWV IQ section, which is also enabled. It outputs IQ streams on a different multicast stream than the AM demodulated streams. It has the AGC turned off. That's very useful when you want to be able to measure the amplitude of the carrier. If you were to turn on AGC, then the AGC would change the amplitude of the carrier and you wouldn't be able to make accurate amplitude measurements. The gain is 40 dB, which prevents clipping on strong signals. The sample rate is 16,000 samples per second. The mode is IQ, so it puts out I and Q separate data streams. And it's the same frequencies as the previous one, but they're identified differently. In this case, 2,500, meaning 2.5 megahertz, and so on for the rest of the channels. The frequencies can be identified either way, the K indicating kilohertz, or an M indicating megahertz, or no suffix indicating hertz. There is a concept in ka9q radio called the SSRC, and this is the source selector. Source selector is not an IP port number. It's a unique 32-bit number embedded in the multicast stream that identifies a particular channel. The receive client selects which channel it wants by using the SSRC to identify the channel and using the multicast stream name. So for our application, we happen to have some channels on the same frequency, and that's okay. We have different demodulators demodulating the same channels, and there's no conflict in doing that. The SSRC mapping rule is an embedded letter is deleted. So for example, 10,000 K or 10,000 kilohertz, which is from the AM mode of our example, tells the source to select 10 megahertz, but the SSRC is assigned a value of 10,000. So if we go to the PCM.local stream, we will use an SSRC of 10,000, and it will be an AM decoded or demodulated opus coded signal. 10 million is also a valid SSRC. In this case, it's in the IQ multicast stream. So here we have WWV AM on one stream and IQ on a different stream. In the first demo, we're going to listen to AM demodulated signals from WWV. We, in fact, can listen to all of the ones identified in the configuration file, WWV and CHU. We will start up the server by changing on the server using SSH to the ka9q radio directory, and then we'll invoke the radio D program and our radio D configuration file, a copy of which is on the server. Then over on the client, which is our Linux PC with a mouse and a display, we'll also change into its ka9q radio directory, just using a local terminal on the client. And then we'll execute the monitor program, and the monitor program will let us listen to all of those WWV PCM streams, or all the channels on the PCM stream. ka9q radio codes each AM channel using an opus audio coder, which reduces the multicast bandwidth. The opus coder does not produce a waveform format, it produces an audio coded file. And the monitor program in ka9q receives those opus coded streams, and then it decodes them and produces a waveform file, which can then be sent to the audio card on the computer. This is demonstration number 1, where we'll bring up the ka9q software on the server, and then we'll listen to the AM demodulated channels. So the first thing we'll do is to bring up a terminal window, and we'll SSH from our client here over to the Raspberry Pi. And the first thing we need to do is change into the directory that has the software. And now we can invoke the Radio D program. And this will bring up our modified version of the program. So here we can see what's happened in the output from the terminal. It loaded the configuration file, found the RX888 receiver, that it's got a USB interface, set the sample rate at 64.8 megahertz, pretty close. And then the first section that processes is the WWV section, which uses AM demodulators. So it brings up identifies the SSRC, the frequency for all of those channels. And then it also starts up the WWV IQ demods. We won't be using those in this first demo, but we will use those in the second demo. Now that that's started, let's bring up a terminal window, which is on our local machine here. And we're going to want to monitor the WWV-PCM local stream. And here we can see it brings up all of the channels, and it's listening to all of them, and we'll hear all of them at the same time, which can be a little bit of a mess. So we may want to mute a few of these that are noisy this time of day. And so if we highlight the particular channel in monitor, and then we can hit M to mute or U to unmute. So let's mute the CHU signals, which are sometimes difficult on the West Coast, the low frequency WWV signals, and we'll listen to some of the higher frequency ones, which may sound a little better. So let's listen to the 10 megahertz WWV signal now. So we've now muted 10 megahertz. We can listen to the 15 megahertz signal by unmuting. And there we can tell it's a little noisier. We can try the 20 megahertz signal. And the 5 megahertz signal, which is pretty noisy. So the monitor program lets us listen to one or in fact all at the same time of the signals. And we can exit the monitor app by hitting Control-C. In the second demonstration, we're going to display information about each of the WWV IQ channels. This demo will display WWV and CHU signals from the WWV-IQ section of the config file using a linear IQ demodulator. The example that we have will use gnuradio to let us visualize a waterfall of the carrier within plus or minus 8 hertz of the carrier frequency, the magnitude of the carrier within 8 hertz of the carrier frequency, and that's very heavily filtered with a low-pass filter. We can look at the time domain of the entire 8 kilohertz sample rate IQ channel, so a frequency from minus 8 kilohertz to plus 8 kilohertz around the channel center frequency, and then the frequency spectrum of the whole channel. Here on the server, we'll use SSH to change to the radio directory and then start the configuration file. And on the client, we will launch the ka9q wwv-iq.grc or gnuradio companion gnuradio file. We can either double click the grc file or we can launch gnuradio and then open the file itself and then run the flow graph. This particular flow graph will let us look at a single channel at a time, but we can select which channel it is that we want to look at. And then we can visualize those 4 different methods we talked about earlier on this slide in a separate tab. For the second demo, we're going to use gnuradio to display some properties of one of the WWV signals. We already have started up the server as we did in demo 1, and so here we'll just focus on gnuradio. We don't have any application in the terminal that we run on the client in this case. We'll just run gnuradio. The file ka9q-wv-iq.grc is a gnuradio companion file. We'll double click it to launch the application. And here it brings up the flow graph. We'll walk through the flow graph a little bit. We have the sample rate up in the upper portion set for 16 kilosamples per second. And the RTP source is Franco Venturi's GR-RTP module. We're going to select the SRC of 10 megahertz, so we'll be listening to 10 megahertz WWV. That signal goes through a constant multiplier, so just a gain of 20 dB, factor of 10 in voltage. It goes to a time sync, which lets us look at that 16 kilohertz on an oscilloscope display, on a spectrum analyzer display, and then we'll low pass filter that to 6 hertz, which will be minus 6 hertz to plus 6 hertz of the channel frequency. And then we'll decimate the sample by a factor of 1024, because with a 6 hertz bandwidth, we only need a 16 hertz sample rate. We'll then send that to a waterfall sync so we can see the amplitude versus time on our waterfall. We'll also extract the magnitude of what's in that plus or minus 6 hertz signal, essentially just the carrier. We'll smooth that with a very low alpha single pole IIR, or infinite impulse response filter. We'll take the log of it so it will display in dB, and then we'll go to a time sync so we can look at the magnitude of the carrier frequency over time. The time sync is capturing 16,000 samples, which at a 16 hertz sample rate will be about 20 minutes worth of samples. In gnuradio, the time sync doesn't display until it's captured the entire time buffer, so we'll have to wait about 20 minutes to see that. In the upper part, we'll take the signal from the gnuradio source and we'll multiply it by a signal source of 1.5 kilohertz. That will shift it up in frequency. We'll low pass filter it to plus or minus 1.35 kilohertz, and then we'll multiply it by the complex conjugate, which will shift it right back down. That has the effect of selecting only the lower sideband and rejecting the upper sideband. This is called a Weaver demodulator. We'll then extract the real part, we'll increase the gain, and we'll send it to an audio sync, which will allow us to hear the audio of that signal. We have a tab widget, and we've selected each of the 4 displays to go into a different tab on the tab widget. So we'll bring up now, we'll run the flow graph, and we will enable the audio for the flow graph.
35 minutes, coordinated universal time.
This display shows the frequency spectrum of the channel from minus 8 kilohertz to plus 8 kilohertz. You can see the carrier in the center, and then occasionally when there's modulation, you can see the sidebands pop up on the spectrum. The transform's about 1024 samples in the FFT, and further, there's an averaging control up on the legend here that will allow smoothing out or averaging a number of the spectrum. Generally, the sidebands will sort of disappear when you do that, but the noise will become quite a bit less. And then in the scope display, this shows the IQ waveform of the channel, the plus to minus 8 kilohertz channel in the time domain. The I and the Q waveforms are about half a hertz, and that's due to an offset error in the local oscillator or the timing oscillator in the RX888 receiver. Additionally, there can be some errors due to Doppler shift on the received carrier from WWV. Sometimes you can even see 2 different carriers, one from WWV and one from WWVH, although those are usually only resolved in the carrier waterfall. The waterfall takes a few minutes to accumulate a significant number of samples so that you can see what's going on, and the magnitude display takes about 1,000 seconds or so to accumulate enough samples to trigger the display. The oscillator in the RX888 is pretty good. It's on the order of about half a part per million on the unit that I have, and it's temperature compensated, so it seems to hold frequency fairly well. To get more precise measurements, an external frequency reference is needed, and the RX888 has an option to do that. Okay, about 20 minutes has elapsed, so we've now captured some data.
0 hours, 2 minutes, coordinated universal time.
Now if we look at the carrier waterfall, here we can see the span is going from about minus 8 hertz to plus 8 hertz, 0 being the center frequency of the channel. And you can see that there's about a negative half a hertz error, and that's due to a couple of things. One of is the error in the local oscillator in the receiver, and some of it is due to Doppler shift. The time scale is not accurate on gnuradio at these sample rates. We can also see the 1 hertz ticks on the carrier. Sometimes you can see splitting of the frequency due to hearing both WWV and WWVH at the same time. If we look at the magnitude, this is the magnitude over about 20 minutes, and the scale here is relative dB. You can see when that very low alpha IIR filter starts, it has to charge up, and so there's a fairly long time constant. The signal variation here is from about 5 or so up to about 16, so there's about a plus or minus 5 or so dB variation in the signal strength on WWV. So this is a very useful flow graph. It lets us look at a couple of different aspects: the spectrum, the magnitude, the time domain signal, where the 1 hertz ticks are pretty readily apparent, and the waterfall. The third demo, we're going to record WWV IQ data using DigitalRF. This demo captures the signals and stores the data and metadata in an HDF5 or hierarchical data format version 5 container. Again, on the server, we'll invoke Radio D in the configuration file. On the client, we'll launch ka9q-wv-iq-digitalrf.grc gnuradio companion file, and we have to tell it where or what directory path and directory name we want to store the collection of data generated by DigitalRF. HDF5 puts all of the data into a single directory, which is a container containing multiple files and other directories. For the third demonstration, we're going to capture WWV on 10 megahertz IQ samples to the DigitalRF format. As in demo 1, we've already SSH'd into the server, changed directories, and started up the HF configuration script with the Radio D command. Here we can see we have an empty directory DRF example, and we will go ahead and launch a different gnuradio flow graph. This particular flow graph is the WWV-IQ-DRF. Here the RTP source is set to 10 megahertz, and it goes to the Qt GUI time sync so we can see the IQ samples. It also goes to the DigitalRF channel sync. And in the channel sync, we've set the directory home/toms/desktop/DRF example. We've then set the metadata to 10 megahertz. We also have the audio lower sideband signal going to the audio sync so that we'll have something to listen to while it's capturing. We can now start the flow graph. And here we can see the IQ samples.
At the tone, 0 hours.
And we can also hear the WWV audio. We've now stopped capturing data. We can close the flow graph. And if we go into this folder here, we can now see that we have a file with the properties, with the metadata in it. And we have the actual time samples that we had set the cadence to 1 second. So we have a separate file for each 1 second of capture in DigitalRF format. If you're interested in the DigitalRF package, a description is located on the MIT Haystack GitHub repository, which also contains the gnuradio DigitalRF module. That module records the data in the HDF5 hierarchical data format version 5, and a description of that format is on the HDF group organization page. I'd like to say thank you to Phil Karn, ka9q, for the development of the ka9q radio software package and for Phil's help in getting started. I'd also like to thank Franco Venturi, K4VZ, for his development of the GRRTP real-time protocol out of tree module for receiving the multicast streams in gnuradio. And lastly, I'd like to thank HamSci, the Ham Radio Citizen Science Project, and the principal investigator on the various HamSci projects, Dr. Nathaniel Frizzell, W2NAF.